gentlemen, good morning, good afternoon, good evening to all the participants who are logged in from Europe, Middle East, India, Sri Lanka, Bangladesh, Thailand, Indonesia, Australia, and China. I welcome all the participants for Plastic Flame Retardancy Learning Series number 2, conducted by Formulated Polymers Chennai, Eurostar Engineering Plastics France. This webinar is for all practicing professionals in electrical and electronic industries, auto, solar panel, and EV, etc. This series has 2 parts. One is for 35 minutes of webinar and 10 minutes for question and answer. I am Krishnan. I am the head of materials in Formulated Polymers, and
the slide is not moving.
Slide is not moving. I'll just stop the slide. Sorry, just give us a sec. Sorry, there is some technical glitch. I am Krishnan, head of materials in Formulated Polymers. This webinar will be
my screen.
Can you able to see the screen?
Yeah, we are able to see.
Good. So this webinar has been broken into 2 parts. 35 minutes is for presentation and 10 minutes for the question and answer. I request all the participants to post their questions in Q&A box and not in chat box. This webinar is more of practical in nature, not on theory. As part of our learning series, we have already conducted the first series on history and need for FR in last month, and the repeat was also done due to overwhelming response was done on 20th of July, and that was a successful program. And we have lined up quite a few programs like testings of FR. We have part 1 and part 2, and we have the webinar for standards, how to read the standards, the process guidelines for FRs, and the environment impacts of FR, and the post care for laser marking and pad printing. I request the industry experts, professionals to come forward to present in their future learning programs. And since Eurostar and Formulated Polymers Asia specialize in compounds of engineering plastics, all the examples will be based on polymides, ABS, and PP. Coming to the speaker, I would like to introduce Alex Chopin. He is a technology manager from Eurostar Engineering Plastics France. He has done masters in plastic engineering from France. He has more than 25 years of experience. He is an expert in subject knowledge. He is a co-applicant to many patents in FR engineering and is a subject specialist in low voltage and medium voltage for FR designs and sections. Today he will be handling FR mechanism of halogen and phosphorus based FRs, and he will discuss their merits and demerits in today's session. Ms. Rashmi will take part for the second part of the webinar, and Ms. Rashmi is a Vice President Development in Formulated Polymers, and she has more than 29 years of experience, and she is a PhD holder and from polymer technology from Delhi University. She has presented many papers both in national and international forums, and she has a Six Sigma black belt. She will discuss about the flame retardant mechanism of metal oxides and other systems, and their selection criteria and their merits and demerits are in the today's session in part 2. Just to have a quick recap for those who have missed out for the first series, where we have discussed about the history of plastics and FR and the reasons why the FRs has been used. Alexi has given us a great example of identification of FRs using ISO standards, were already discussed during the previous webinar, and the details are available in the YouTube. For the participants who are able to go and check, I request the participant to put Formulated Polymers web series there we can able to find in YouTube. The link is also given in the link so that you can take note of it. In this webinar, we will be discussing about the halogenated compounds, nitrogen, organic, phosphorus, and inorganic compounds. Now, I hand over the webinar session to Alexi. Alexi, please take over. One sec, I will stop my recording.
Okay, so thanks a lot, Unicreation, for giving us the opportunity to share a bit of our knowledge on flame retardancy. Because yes, as both company has a tremendous experience in flame retardants of plastics. So let's start with the most famous one, or at least the most in use one, is halogenated flame retardant system. You will see there is a bunch of systems to flame retard plastics, but halogen is still, let's say, the more in use in volume and the more common. And don't overlook, flame retardant for plastics is a huge market, and flame retardant is over 1,000 kilotons used in the world, because there are flame retardant everywhere, can be in plastic but also in cables, and so there's now let's say a 30 years experience on those one. And to stick to halogen systems, halogen is a world, in fact. Halogen, you know, it's 3 elements. It's 4 elements: fluorine, chlorine, bromine, iodide, and these are heavy elements. And among that, at least 2 of them are really in use for flame retard plastics: chlorine and bromine. Chlorine is, let's say, in use now for let's say, polyolefins. But with sorry, can't you hear me?
Are you sharing any slide, or you are?
Alexi, you're not able to see your slides.
Oh, let me check. Theoretically, share the screen. I think I will be ready at the end of the series.
Yeah, now we are able.
Okay, now. Okay, so sorry for this. Okay, just say that halogen compound is a world. Let's say there are a lot of material. Some of them are, let's say, respectable. Some of them are not. Everybody hears now about the decabromo ban. So it's one which is no more in use. Maybe it's still in use for some application. But within this range, you see, according to the ISO 10043 classification, you have all of those choice of possible possible elements. Some of them are no more in use, but some of them are really in use. And most of the time, 21 is in use. It's a combination of a brominated system with antimony trioxide. I won't go too much into details today, but what is important to understand is that halogen is really acting as flame retardant, not itself, but in synergy with antimony trioxide. So, as mentioned previously, this is a very well in use system, a very well known system, so it remains something that you find on the market very easily. So what are the strengths for this one? The strength is the duration of use. It's very easy to formulate, it's very reliable, and it's a system that can work with, let's say, almost any filler or combination. We will see after that it works in the gas phase, so meaning that it's a physical shielding of the flame. So you will find application, say, filler possible. It can be glass fiber, it can be mineral, it can be mix, it can be combination of those ones. The good thing is, as it works only in synergy with antimony trioxide, or mainly, antimony trioxide helps a lot for laser marking. So you can have a very nice contrast, especially dark marking on light colors. The good thing is also that it's very versatile material. You can flame without almost the complete range of nylon, of polyamide. It goes from 6, 6, 4, 6, PPA, 12. It works everywhere, and it's a real proven solution. So this is the strength, and don't overlook, it's a very well in use material, and it's still a living material. In some cases, you know, we'll explain there is a trend to phase out those brominated systems due to ecological, let's say, concerns. In some cases, they are very difficult to phase out because the carrier of this bromine in the formulation is very often an aromatic ring. It can be polystyrene, for example, and it brings a kind of amorphous phase in the compound, meaning in some cases it reduces slightly the moisture takes, and it gives a more isotropic shrinkage. The weakness, what are the weaknesses? Because there are some. It's quite an old product. And is it really an eco product? Yeah, it depends on the pole. But in some cases, it's considered as non-eco, not so much because of the bromine, but due to the synergist. Antimony trioxide is more and more concerned in our world. Another drawback is the limited current tracking index. For those which are non-specialists, this is the electrical properties of a compound, meaning that it's very difficult to go above 400 volts. So there are mainly applications that are not too close to the arc. Processability is sometimes a concern, but with new material, it's almost okay. When you go to real drawbacks, is that when it's processed in overheating conditions, for example, it can release acids while burning. And acid is very corrosive to metals. And most of the case, when you are using a flame retardant plastics, is to protect an electrical device. It can be a car or an electrical. And the damage caused by the burning can go up to the connection, for example. And it's a material which really fumes dark and heavy. You know, when you burn, or try to burn a material which is flame retardant with a halogen system, you feel it immediately because you see this fluffy fumes, which is it's a very acre smell. So it's not an easy one. For example, in new regulation for transportation, this is really not the material to be used. You need a quite high loading to flame retardant material. Let's say if you make the sum of flame retardant system with antimony trioxide, meaning its synergist, it's above 20%. So it has a real impact on mechanical properties. In some cases, it reduces the melt flow. So I will go a bit into the systems, but not, let's say, going too much into details about chemistry. But what you have to know is that it's working on the gas phase. While burning, it creates free radicals that combines with, let's say, the antimony and creates very heavy smokes that insulate the polymer from the flame. We could go more into details if you want after that, but I think it's not the topic of today. Huh? And when you see molecules, let's say, of brominated material, it's always complex molecules with an atom of halogens. And what makes the efficiency of a molecule is the amount of bromine. For example, in polyamide, we are using often brominated polystyrene or polybromostyrene, and the amount of bromine in the formulation is above 60% in weight. The molecule itself is a powder from a chemical industry. And from this, Form Poly and Eurostar made a complete range. And in this slide, you see only a few examples of those ones. You see here a polypropylene from Poly, an ABS, nylon 6, nylon 6,6. But it's far broader than this. In both companies, we are able and we are already providing formulation based on PA46, on PBTs, on a lot of material, nylon 11, 12. So I think I already have to speed up a bit. So go to the next range, or let's say, maybe let's take a few seconds to this one. So this is the more in use material, way to flame retardant plastics, but it's challenged. Why is it challenged? Because in some cases, I don't know if you see this one. No, sorry. Maybe it will be better, this one for you. So many studies were made showing that we have more and more synthetic material in our houses due to electronic device, due to equipments. And one thing is very important is the escape time in your flat, for example, dropped from 17 minutes in 70 to 30 minutes in 2007, meaning that with the fumes and the heat generated, our homes are less and less safe. And another hot topic for this one is, let's say, recyclability. Recyclability is a real concern in modern countries because we have to take care of what we will let to our children. And there is a principle now which is in use, is polluter pays principle, meaning that who plays on the market the material has to be responsible for it. So from now 20 years, we are fighting to have, let's say, halogen-free systems. The more in use is the nitrogen base, so it's mainly melamine cyanurate, so the ISO code is the 30. So it's a very efficient material. System cost is really good. You can make almost any color, so you can have very bright white, laser marking is possible. When you see the molecule, this one is melamine cyanurate. Be careful, don't use melamine, because melamine is less stable and is water soluble. But this one is stable up to, let's say, 320 degrees C, so it can really be used in polyamide or in other polymers. It's really still a chemical product from chemical industry. The weakness of this product is that we'll see next page, is a dripping system. So it works very well for UL94 V0 only for non-reinforced products, meaning that it's limited in modulus and processability might be a concern. So once more, I will not go too much into details about and question about how it works. It works everywhere. It works in the gas phase, it works on the condensed phase, mainly in the condensed phase. But let's say to understand how it works, I love this chart, People who are aware of UL testing, you burn a material for 10 seconds, you remove the flame, you add another 10 seconds, and after you see how it behaves. Melamine cyanurate has a strong acid in burning. It decomposes the polyamide, then creates droplets. And these droplets are very small and escape the polymer from the fire and escape the heat from the sample. This explains why it works very well for very thin material, up to a very low thickness. We have V0 listed up to 0.4 millimeter. No, but if material is loaded with glass fiber, then you have too much heat concentration and the material stays a real flame retardant, meaning that the combustion time is very low. But nonetheless, in some cases, you might have a flammable drip that makes the material V2 material. So I will not go too much into details about molecules, but melamine cyanurate is a condensation of melamine with cyanuric acid. So you see you have absolutely no halogen on this formulation. The market for those one, as the material is not too stiff, is mainly connectors for unfilled material and circuit protection. But you can also find those type of application everywhere, even in medical application. From this, we have a very extensive range, or in Eurostar or in FPL, and you can find unfilled material filled with fiber, with mineral, with volastonite, with mixed, based on different polymer, 6 and 6,6. So this is a very nice and up-to-date range with V0 down to very low thickness and a good RTI. Then you say, yes, now we have, with melamine cyanurate, we are in the world of enclosure, we are in the world of, let's say, boxes, connectors, but when you need a more stiff material, a material which is close to the arc, where the fire is, sometimes when you cannot use halogen flame retardant, you can use phosphorus-based material. So with phosphorus-based material, you typically have two different systems. You have, let's say, the more common one still today is the red phosphorus with an ISO code of 52, and you have organic phosphorus compounds with an ISO code of 40. So the strength and the weakness here adapt mainly to the red phosphorus one. So phosphorus is red naturally. So phosphorus, everybody knows, it's what makes the material burn in matches. When you light up your cigarette, you use a match, and to make it burn, it's a phosphorus. So it's a very material which is reacting very well with fire. And of course, it's a burning material, but in some cases, when it's at the right level, it's really flame-retardant plastics. So the material itself is red. You don't need so much to flame-retardant plastics, about below 10%. So the system cost is very interesting. The property profile is high, and the impact on the other properties is really low. You can go up to 50% glass fiber with material. It has still very good electrical properties, and density is low. Some possible concern is phosphine emission. I say it was very true in the past years. Now, under right processing condition, it's not something you have to fear too much. It can be very well controlled. Color capability indeed is a problem, because as the raw material is red, you can only have material which is black, natural red, which is not true. In some cases, we can make dark blue for some customers, and it works quite fine. Corrosion might be problematic, and material handling is a problem. It's a problem mainly on the manufacturing side, but when it's in form of granules, it's no more a problem, let's say for mortars. So this was for red phosphorus. But let's say the novelty above those last year is the use of halogen-free phosphorus compounds. So there we are using molecules which are always phosphorus derivatives. So you see in all those molecules phosphorus atoms, let's say, no more chlorine, no more nitrogen as a melamine. So this is the best way to, one of the best way to replace halogenated formulation when you cannot use it anymore and you need some stiffness. And for example, the color is white, so you cannot use red phosphorus. So these ones are really very effective. They are working typically in the carbonization, in the condense phase. How they work? They are called intumescent system, meaning while burning, they create a strong char on the surface of the polymer and insulate the polymer from the air or the oxygen. So this char is preventing the fire to propagate. So these are not, let's say, very simple system. These are most of the time, let's say, system of flame retardant. Binary or ternary system. The most famous one you are using is a combination of melamine polyphosphate with a metal phosphonate, which is in some cases aluminium zinc phosphonate, and a synergist that can be, for example, zinc borate. So these are very, let's say, formulation which are up to date, halogen-free, and which have mainly advantages. It's difficult to find drawbacks for this formulation, except that they are quite new, except that they are somehow sometimes more expensive than the other one, but it's typically the material we dreamt of formulating for 20 years. Now we see, for example, on this page, that we are able...
we are running short of time, so I would request you to run through it.
Okay, so yeah. But basically this one is very important. I will go fast now, but we can make V0 down to 0.5 millimeter. You can have continuous in use temperature of 150, very high modulus. And from this, we have a real nice range at Formpoly and Eurostar of material, which are UL listed in 6.6 with glass fiber from 20 to 45%. And it's really the more, let's say, up-to-date formulation for us. Melamine phosphate, I will go very fast because this one is a kind of derivative of the previous one. It's just pure melamine polyphosphate, and the single interest of it is that it passes the GWIT for people who are working for appliances, what we call white goods. So I think now I can just give the talk to someone else. I hope I have not been too long and too complicated.
Yeah. Thank you, Alexi, for your wonderful presentation and giving us the reasons for using FRs, especially nitrogen, phosphorus, and new generations, and why it has been used. What are the advantages and what are the disadvantages? And it was good. It was an eye opener for people like me who were hearing a lot of FRs, but we don't know why and what purpose they are using it. So thank you very much. And I once again request all the participants, please post your questions, I think, in Q&A box, so that once the webinar is done, we can have the question and answer. Over to Rashmi now.
Yeah, I'll share my screen. Thanks, Unikrishnan. Oops, what happened? Can you see my screen?
Yeah, please go ahead.
Okay. Thanks, Unikrishnan. Alexi has just discussed the mechanism of halogenated nitrogen, organic and inorganic phosphorus compounds. I will be discussing the mechanism for metal oxides, hydroxides, and metal salts, the boron and the zinc compounds, the silica compounds, and some specialty ones like the polyvinyl alcohols. The role of the flame retardant is to make the polymer formulation less flammable by interfering in the chemistry and physics of the combustion process. FRs are effective at the growth stage of the fire. Emphasis is on reducing rather than eliminating the fire, as all FR formulations will ignite under extreme conditions. Primary concern when selecting a FR system is the end use application. It's very important that we decide which application we want to use the particular FR system. We shall be discussing the present trends, the selection criteria, and factors responsible for selection of the FR systems. ISO 1043 gives the symbol number to FR added to plastic substances that retards propagation of the flame. And here the numbers have been given. So I will be discussing numbers 60 to 80. The reaction can be endothermic reaction, that is, it requires absorption of heat, as breaking a chemical bond requires energy. It can involve radical quenching or inhibition, where it neutralizes the free radical. And the third process which we are looking at is thermal shielding, where it forms a barrier which acts as a protecting layer and prevents the flame to spread very fast. So metal-based FR systems, mainly it comprises of aluminum hydroxide, magnesium hydroxide, antimony trioxide. Then there are certain salts like the alkali metal antimonates, magnesium calcium carbonate hydrates. So the best part about these metal-based systems are that they are non-corrosive. Alexi discussed the halogen systems. These are basically halogen-free systems, and they are environmentally friendly. They are inert and non-volatile, and they hardly have any impact on the color. And of course, they are easily recyclable, and they have reduced smoke density. So if we look at the strength of these systems, then there is very low smoke emission. The FR properties like the glow wire is 960 degrees, and UL rating we can achieve up to V0. Very high CTY values of around 600 volts. Mechanicals are also very good, very high modulus, and dimensional stability also is its strength. Now, when we come to the weakness, then it requires a very high loading. More than 50% loading is required of these metal hydroxides. So it's high density, so part weight is also higher in this particular case. It impacts the elongation because of the high loading, and of course, compounding is a challenge. The major polymers where metal-based FR systems are used are polyolefins, thermoplastic elastomers, vinyl chlorides, rubbers, thermosets, and also in polyamides. Now, if we look at the processing temperatures, in case the processing temperatures are less than 200 degrees centigrade, then we used aluminum trihydrate. And in case the processing temperature of the polymer is more than 200 degrees centigrade, then we use the magnesium hydroxide systems. The basic mechanism is decomposition, where it's an endothermic reaction. It produces water vapor, which dilutes the flammable gases. And of course, there is some adsorption so that the combustible gases are reduced and smoke also gets reduced. The protective mechanism is the char formation and the smoke suppression. Here we have given a couple of examples. The main thing here is that there is water which is released. So whether it's the aluminum trihydrate or it's the magnesium hydroxide systems, in both the cases, water is released. And if we consider the FPL products, then we have the magnesium based system, which is RF0023 star flame grade. Next, we come to the borate based systems. They comprise of inorganic and organic boron compounds and zinc borate systems. I'll be discussing over here the zinc borate systems. And then we also have the organic zinc compounds. The organic compounds, of course, have, like boron will have the boron carbon bonding, whereas zinc will have the zinc carbon bonding. So these have been adopted by the plastics in the industry as a synergist. They act as a synergist and are very effective when they are in combination with another material. So boric acid and borax have been used in the cellulose and cotton industry for a very long time. Zinc borate has been used in vinyl chlorides, olefins, and polyamides. Here also what we see, it's an endothermic dehydration reaction with the release of water. So water is released. And char formation and char stabilization is due to the halogenated part of the system. So formation of a glassy ester coating, which acts as a heat shield when it's combined with ATH, is what gives it the synergistic effect. The boron trihalides like PCl3 is formed over here. This acts as a Lewis acid and basically it promotes the cross-linking. So in a way, it helps the flame retardancy of the material. Then another system which we are considering is the silicon, which is a very eco-friendly system. You have the inorganic silica compounds and the organic compounds, which are normally the silicones. These are ecologically safe flame retardant systems, and they act basically in two ways. One is the formation of a protective layer, like you have the barrier which is formed over here, which reduces the thermal conductivity of the material, and as a result, it enhances the fire resistance. And the other part is the trapping of active radicals in the vapor phase, so it inhibits the gaseous phase combustion also. So if we look at the mechanism, it's postulated over here. You have the silicon, you have lead chloride at around 350 to 500 degrees centigrade. It results in the formation of tetrachloro compound. Now this in the presence of water gives us the HCl. So HCl is not so good, but since the dosage is very less, it is comparatively eco-friendly if we compare it with the halogenated materials. So certain halogen halides are used along with the silicon compounds. This is an example of a polycarbonate filled, glass filled, mineral filled material, and it is based upon the silicon flame retardant system. Then we have the polyvinyl alcohols. Here also there is a formation of a barrier char which hinders the supply of oxygen and reduces the thermal conductivity. Water is split off from the polymer. So at around 245 degrees centigrade, it releases water. So almost all the systems which I have discussed, there is a release of water. And here with polyvinyl alcohol, if we consider independently polyvinyl alcohol and polyamides, then there's hardly any char formation. But then when you use it as a combination, then it gives synergistic carbonization, and char yield and flame suppression is much better. As an example of a silicon system, let's consider a polypropylene. So we took polypropylene and we had a polypropylene with silicon and SnCl2. So the ratio is 95:3:2. So when you consider this, then char yield, when we take pure polypropylene, char yield is negligible. But when we add our silicon and lead chloride systems or tin chloride systems, we have the options. So then it increases up to 10% yield. Ignition time also increases from 62 seconds, it goes up to 91 seconds. And the other major advantage is the peak rate of heat release gets reduced to almost half. And the total heat release, if we look at it, gets reduced by almost 40%. So there is a substantial improvement in the flame retardancy of these systems, and they act as synergistic systems. Then we come to the current trends. The trend is for halogen-free flame retardants. Normally, these flame retardants, which are halogen-free, are safe, and there are few issues or concerns which have been identified. If we look at the aluminum hydroxide system, or we look at the zinc stannates or zinc hydrostannates, these are organic, inorganic substances, and they have very low acute toxicity. So, and they are chemically very stable also. So they are considered as one of the safest systems which we can use as flame retardants. Then there is a certain level of concern when we consider RDP or bisphenol diphosphates, resorcinol diphosphate. So here the toxicity to aquatic organisms is the main concern, and that has been linked to the impurity. Like if we consider the TPP impurity in the RDP, so then that might be the reason for the toxicity of these. Then, of course, our main concerns are regarding nanoclay, and nanoclay can be due to the nanoparticle coating. So it shows a strong in vitro neurotoxicity. So these are like some of the concerns, but then we have a good list which is safe and which is having very few concerns. Over the period of time, if we look at how the flame retardant systems have evolved, earlier flame retardant was just that we wanted to get the flame retardant properties. So brominated flame retardants, red phosphorus was there. But then subsequently, as awareness increased and as we had some accidents, some issues, the toxicity and smoke became critical. So then there was an evolution in terms of melamine cyanurate, magnesium hydroxide. But then these days, the concern is mainly on the environment. So although there is an evolution, like if you look at the application, a simple application has evolved over the years, and there is a lighter, thinner, higher mechanical requirement for the material also. So the overall eco-FR building blocks have become more and more important. Now, coming to the flame retardant selection criteria, we have considerations like the flammability, whether we want a V0 material, we want a V1 material, and then of course, efficiency and cost also change, like we want V0, cost by default goes up. Then another critical thing is the thickness of the application part. It should be meeting the requirement at that particular thickness. So if it's 0.4 mm, then it should be meeting the V0 requirement at 4 mm itself. And then there are the appearance requirements, because aesthetics are critical for any application. And of course, we have to see the FR effect on other properties. The mechanicals should not drop. There are other properties like the electrical properties should not get impacted. And another factor, which I'll be also discussing in my subsequent slide, is the compatibility with polymer and the processing of these materials. Eco concern and environmental, especially on smoke and corosivity issues, are also some factors which impact the selection criteria. And we have to take into consideration all these factors when we want to decide which flame retardant system we want for our polymer. This is the polymer compatibility chart. We have, like, on one side all the polymers, ABS, HIPS, polypropylene, the range, and then we have the flame retardant additives. It's not that you can use one polymer and use any of the flame retardant additives. There is a compatibility, and these evaluations have been done, and this data is readily available. Now, if I consider a polycarbonate, then it requires tetrabromobisphenol A or brominated diphenyl oxides. But then if I consider ABS, then it can be used for both these and tribromophenol also. But then it cannot be used by dibromostyrene derivatives or tetrabromophthalic acid. And this impacts the system which I decide when I make a blend. So if it's a ABS PC blend, then I have to take into consideration what is compatible with ABS and what is compatible with PC, so that when I make a blend, the FR should be effective in that particular system. And this same is applicable to other systems like polyphenylene oxide is basically a blend of HIPS and polyphenyl oxide. So here also there is a decision which has to be made. HIPS has a range. Like there are a number of additives which are compatible with HIPS, but if you consider PPO, then there are very few. So for modified PPO HIPS blend, then we are limited by just maybe triaryl phosphate esters and bisphosphonates. And of course, it's a total world of regulations. You have the technical regulations, whether it's a UL, the Bureau of Indian Standards, or the IEC, or the Chinese CCC standard. There are certain environmental regulations also. You have the ROHS, WE, eco-labels are also there. So we've got to take into consideration all this and also have the certifications. And normally these certifications are for the application. I won't be discussing in too much detail regarding the world of regulations because we have a total session dedicated to this. We will be discussing in detail what are the parameters which have to be taken into consideration, what is the type of evaluation, application, as well as product evaluation which is required. And we will have a full-fledged session on this. But this is a very important criteria when we are making a decision as far as which flame retardant and which polymer we are deciding upon. This is actually, Uni was discussing with me yesterday and he said, I'm talking too technical. So he wanted it to be a little bit easier. So we made a chart where we have the brominated systems, we have the mineral fill systems, we have the red phosphorus and the eco-FR. Now, if I consider the brominated system, so smoke is high, corrosion is high, mechanicals are comparatively on the lower side, electrical properties are superior, processing is a little bit difficult, and sometimes color is an issue. Then you have the mineral systems. I've discussed the mineral systems with you, the aluminum trihydrate, magnesium dihydroxide systems. So here processing is much easier. My internet is unstable. Oops. Yeah. Processing is much easier in these particular cases, but corrosion is low, smoke is low, mechanicals are more or less met with. Electrical properties are, Alexi has discussed the red phosphorus systems. Here corrosion, smoke is comparatively lower, mechanicals are totally achieved, and electrical properties are also superior. This is basically an example where we are considering maybe a V0 system. The filler content in all of them will be different because the mineral fillers will be 50% plus loadings. And then we have the eco-FR systems, which we are promoting, and there's a lot of work which has been done by Formulated as well as Eurostar. So here we have a system where we have comprehensive properties which are there in the end product. So electricals are good, mechanicals, corrosion is less, smoke is less, processing is much easier. So if we look at the technical properties, then we have the RTI values, that's long-term aging. We are doing a comparison, the CTI, the comparative tracking index. We have the ISOD notch impact. So there is a variation, and overall what we see is that for the next generation materials which we are looking at and which we are adding as flame retardants, there is a universal property achievement which is a very positive thing and which gives us the strength to go in for far superior and far stringent applications. This is a summary of the FR systems, the red phosphorus systems. They have proven capabilities in electrical, but they are only available in dark colors. So there are strengths, there are weaknesses. We can get a UL rating of V0 at 1.6 mm. We have few examples. I think Alexi has already discussed the examples. Then we have the brominated systems, which are quite robust, but they are halogen based. So limited electrical properties, we cannot use them everywhere. but we have a product basket where we have all these products. The mineral flame retardants have outstanding electrical properties, but limited mechanical properties. Here also we are able to achieve good CTI values of 600 volts, V0 at 1.6 mm. Organophosphorus, glow wire, we've gone up to 775 degrees centigrade. We have the grades which are BDE approved. It is also 1.6 mm thickness and it is UL listed. We have melamine cyanurate grades also, which are in circuit protection. We have certain grades which are V2, we have grades which are V0 also. This is quite a comprehensive product basket ranging with a range of CTI, RTI and glow wire values. Organophosphorus, that's the next generation which we are considering and where we have our strengths. We have outstanding flame, electrical, mechanical properties, and aesthetics are also good. I think laser marking has been observed as an issue as far as some of the phosphorus compounds are concerned, but then that has also been resolved jointly, and we have our products going out and giving very good laser markings. So this is the organophosphorus next gen is one of our premium compounds. So finally, just to conclude, the action of flame retardants, they act by interfering in one or more stages of the combustion process. So the inhibition of the vapor phase combustion, dilution of the volatile products, promotion of char forming reactions, formation of a protective coating, removal of the heat of combustion and smoke suppressants. So it can act in either one stage or in all the stages. So as we move to the next generation, we are looking at some systems which are impacting all the stages. So thank you. I think I'll pass it on to Unikrishnan to continue.
Thanks, Rashmi, for nice insights of the current trends in FRs and why are we using different FRs? Because normally people comes and tell they used to have brominated, dead phosphorus, eco-friendly, but most of the people were not aware whether it okay for the mechanical properties. The mechanical properties is achieved, whether the electrical properties are achieved. If both are achieved, how about the processing and the color? So thank you very much for giving us the overall view of which FR to use for which property. Now we can go to